Hey, good morning, everybody. And this is Mr. Ainsworth. We're going to get into a prep, all right, for 1C2. Okay, so 1C2 prep. And what I mean is just a short discussion here on even and odd integers. Okay, and so this is going to set you up for your activity right here on 1C2. That's what I mean by 1C2 prep. So have your notes out. If you don't, pause the video and get ready here. And let's get started, okay? Let's talk about this. What numbers are we including when we talk about the even number in the integers? So how do we express even integers? So even integers here, or an odd number of integers. I mean, how do we express an odd? Algebraically, formally, and then how do we express an even? How can we formally describe, okay, an even or an odd integers? And so that's the main topic of today, and this is going to get you guys ready for tomorrow in your activity. So let's first talk about the even integer, okay, and write small because we have a lot to do. Okay, so even integer here. Let's split the screen. We have odd integer here. Let's talk about them one at a time. Okay, all right, and write small because uh, we got a lot to talk about. Okay, so here we go. Let's get started. All right, even integer first. Okay, so an even integer is an integer with the following qualities. Okay, and even integer. Okay, by the way, integers. Let's pause right now. So let's put integers up here because you guys were talking about sets and you have to understand what integers are. So they're the whole numbers and their opposites. Okay, no decimals or fractions. So let's start on the left, -3, -2, -1. And then now here comes a whole number, 0, 1, 2, 3, to infinity and beyond, okay? Infinity. And over here, negative infinity. Okay, so it goes there. It's an infinite set, this set of integers, okay? But how do you describe the even ones, like 2, 4, 6, 8, and -2, -4, -6, -8? How do you describe the odd ones, 1, 3, 5, and 9? So you know what? Actually, let's put a few more in here. That's a good idea. So 4, 5, and 6, dot, dot, dot. Okay. So the even ones, the even ones, 2, 4, 6, and the -2, -4. Let's put another one in there. So -4. All right. Those are even. Even there's negative evens too, by the way. I don't know if you knew that. You just might have learned something right there. So you got the evens here. All right, evens. All right, and then the odds. Let me see. 1, 3, 5, -1, -3, and so on. -5. All right, you got the odds here. So how do you describe these formally and algebraically? Okay, so that's what the whole discussion is all about. All right, because you take the evens and the odds and you throw in 0 here, you get the set of integers, but there's certain subsets of the integers like evens or the odds that we need to, sorry about that, and to describe. So how do you do that? Okay, so first of all, an even integer, let's go back to our definition here. An even integer is an integer, obviously, it's an integer, all right, with the following qualities. So with the following qualities. Now, by the way, this is a video, right? So use it as such. You can pause, play, rewind to keep up with me here. So if your writing skills are not as fast as mine, then just pause again and rewind and play and then use your video effectively. Okay. All right. So first of all, everybody should know from grade school that the last digit of an even number is always either 0, 2, 4, 6, or 8. It always, okay. So the last digit, this is an important one, by the way. The last digit ends in either a 0, 2, 4, 6, or 8. All right. If it doesn't end in those, then obviously it's not even, it's odd. Okay. So that's something that you should know back from grade school. Secondly, everybody knows that an even number is divisible by 2. Okay, so an even, okay, number is divisible by 2. Divisible, all right, by 2. Okay, remainder 0. When we say divisible by 2, that means the remainder is 0. So I'm going to make a note of that here. Okay, remainder 0. That's what it means to be divisible. Okay. Um, and then, and here's the key part here. Number three, okay, algebraically speaking, we can always form, or you can always write a number, okay, so it can always be written by, or written as actually, always can be written as a number, okay, as a number n, let's say, in the form of 2k, all right, 2k means 2 times k, okay, where we say k is a, some integer. So for where k equals, some integer. Okay, so if this is the abstract part of it right here, n equals 2k. What does that mean? Okay, so let me highlight that first of all. This is the even form. Okay, we call that even form. Well, why? Okay, so let's take a look at a few examples here. All right, so for example, 8. Okay, 8 is simply 2 times 4, where notice 4 is an integer. Okay, so this integer in this case is 4. 12 I can re-express as 2 times 6, where now the integer is 6. If the even number is 16, let's say, I can write it as 2 times 8. Okay, it could always be written as 2 times some integer. So any even number, all right, can be written as 2 times some integer. Okay, that's the basic form. We call this the form of the number. Okay, the form. 2 times k. So that's an even form. Like 20 is 2 times 10, 100, 2 times 50, and so on. That's even form. You can always do that for an even, but you can't do that for an odd, okay, like 5. You can't say it's 2 times some integer. It'd be 2 times some decimal, so that doesn't work for odds. So speaking of odds, here we go. So an odd number, or excuse me, an odd integer, excuse me, we're talking about integers, an odd integer, got to be specific here in mathematics. So an odd integer is an integer, okay, with the following qualities. Okay, number one, you know from grade school that the last digit has to end in a 1, 3, 5, or 7, or 9. So the last digit must end. Oh, let me clean that up a little bit. The last digit, all right, must end with, all right, 1, 3, 5, 7, 9, okay, only. All right, if it ends in either 0, 2, 6, or 8, all right, it's even. But if it's odd, it has to end in a 1, 3, 5, 7, or 9. These are things that you knew from grade school, okay? All right, secondly, something else that you should know, all right, that if you divide it by 2, the remainder is not 0, like for even numbers, it's always 1. Okay, so when divided by 2, when divided, all right, by 2, all right, the remainder is always 1. Okay, the remainder is always 1. Okay, so let me show you that right there. So let's just give an example. So let's take like 15, let's say. So 15, all right, divided by 2, divide 7 times. 7 times 2 is 14, subtract remainder 1. All right, so we can say that 15 is equal to 2 times 7 plus 1 more, right? 14 plus 1 is 15. Another example, if I take, like, say, 21, all right, divided by 2. 21's odd, divided by 2, divides 10 times, right? 10 times 2 is 20, remainder 1. So I can say that 21 is 2 times 10 plus 1 more. Okay, remember that 1 is remainder. So in general, I can say that odd form is always 2 times an integer plus 1. So 2 times an integer, all right, plus 1 more. Notice this, let me highlight, okay? That's it. 10 is an integer, 7's an integer. Okay, so that's what I'm talking about here. 2 times an integer, all right, plus 1. It's different. So because of that, every odd form or any number in an odd form can be written as 2 times k, where k is an integer, plus 1, Remember, k is some integer. K equals some integer. So the odd form is 2k plus 1. All right, for an odd, even it's just 2k, where k is an integer. So these are the algebraic forms that you have to get used to because there are something called algebraic proofs for certain things. So you have to get used to that. All right, now when we get to proving things. So for example, this is class question 1, this is question 2. Okay, so the second question here is a set of even integers, okay, all even integers closed under addition. Well, let's be specific and make sure you know what the even integers look like, okay? And it includes the negative as well, but we can, so let me write them out. So s is equal to, specifically here, -4, -2, 0, 2, 4, 6, 8, so on. In this pattern, those are the even integers. So even integers have to end in either 0, 2, 4, 6, or 8, just like I said above here. So how do you prove that an infinite set, this is an infinite set, okay? How do you show that an infinite set is closed under addition? Meaning that if you take an even integer plus an even integer, like 4 plus 6, which is 10, that is the results in even integer, okay? An even plus an even gives you an even integer, okay? So how do you show that? Because you can't list them all, because there's an infinite number of examples. So how do you show mathematically that this always happens, that you take any two even integers, whether they're negative or positive, it doesn't matter, and then show that it's closed under addition? Okay, so I'm gonna represent this two ways, or show this two ways. So let's split the screen here. All right, and we're going to talk about two different models. Okay, models or proofs. So model 1 or proof, we call it model or proof. Okay, model 1. And then over here on the other side, we're going to show a different way, model number 2. When I say model, I'm talking about method, okay? Model 1, model 2. So proof method 1, proof method 2. Okay, so you can't list every single case, all right, because it's an infinite set, and there's an infinite number of possibilities. Okay, we don't have an infinite number of time or amount of time, so you got to get creative here. So the first model, one way, is to get creative and use a special diagram that you've seen before. So model 1 is using a diagram to show an infinite number of possibilities. All right, so check this out. Using a diagram, okay, so I'm going to illustrate with you guys, or to you guys here. So illustrate using a diagram, let's put that in quotes, all right, to show, all right, to show an infinite number of possibilities, which is, I just said you can't list them all. So what we need to do is get creative and figure out how to use a diagram, to show an infinite number, all right, of possibilities. All right, so this is cool. Underline the word diagram. All right, and what we can do is use the diagram that we used for the previous examples and when we first started the idea of closure, okay? So we know that when you take any two even numbers, the last digits have to be either 0, 2, 4, 6, or 8. That's the ending digit. So anytime you add two even numbers, whether they're negative or positive, have to end in either 0, 2, 4, 6, or 8. Now notice that I said whether they're even, or excuse me, positive or negative. It doesn't matter. All right, the end digit has to be either 2, 4, 6, or 8. So what we can do is set up a simple diagram, believe it or not. Okay, so let's do this. So I'm going to do what looks like the times table chart that you saw as a kid, okay? But I'm going to use it for addition because we're talking about addition. So the operation's addition. So let's put the operation here. Let's put the plus sign, all right, addition. I want to show that it's closed under addition here. And what I need to do is take a look at the last digit only. That's the key. So ending digit. So I'm going to write that down here. Ending digit. All right, which has to be either 0, 2, 4, 6, or 8. And that's for the first number. The second number I'm going to put on the vertical column. So 0, 2, 4, 6, or 8. And again, this is the ending or last digit. So let's write that down. So it's the ending, or okay, or you can say last digit. Anytime you add two even numbers that end in either 0, 2, 4, 6, or 8, the last digit must be 0, 2, 4, 6, or 8. So you really don't have to look at the entire number, guys. You only have to look at the ending digit, which is cool. So let's take a look at the first row here. Okay, so what we're going to do is we're going to add the two numbers that end in a zero first. So I'm going to take a number that ends in 0, add it to a number that ends in 0. Well, if you add two numbers that ends in 0, then it ends in 0. If you add a number that, now look right here, it ends in 0 and then the other one ends in a 2, then the result is going to end in a 2. You just go ahead and make up, some numbers and try it. You're going to see that I'm right. And then you're going to take a number that ends in 0 and then another number that ends in a 4, and you're going to add them up. And guess what? The result ends in 4 because 0 plus 4 is just 4. And then you take another number that ends in 0 plus another number that ends in a 6. Okay, the result's going to end in a 6. And then a number ends in 0 and then ends in 8. You add them up, and you're going to get a result that ends in an 8, which means that all these numbers, I don't care how many digits they have, from 1 digit to a 10-digit number to a 100-digit number, if it ends with either 0, 2, 4, 6, or 8, it has to be even. Okay, and then you repeat the pattern. So on the second row, let's look down here, right here. If you take a number that ends in 2 and add it with a number that ends in 0, then the result's going to end at a 2 because 0 plus 2 is 2. And then the process repeats itself. So you take a number that ends in 2 with a number that ends in a 2, you add them together. That one's digit is going to become a 4, which is going to make it even. And then a number that ends in a 2 and ends in a 4, then the number is going to end in a 6. And then a 2 plus a 6 is an 8. It has to end in an 8. Now, the number ends in 2 with a number that ends in an 8. 2 plus 8 is 10, so it's going to end with a 0. Okay, so be careful here on this one. All right, 2 plus 8 is 10, so that first digit, the units digit, has to end in a 0, but that still makes it even. Okay, now let's take a look at the third row here. All right, so here we go. So a number that ends in a 4 with a number that ends in a 0 has to end in a 4. Ends in 4 and ends in 2, it has to end in a 6. A number that ends in a 4 and ends in a 4, the other one ends in a 4, the result has to end in an 8. And then be careful here, a number that ends in a 4 and then another number that ends in a 6, 4 plus 6 is 10, so this one has to end in a 0. And then 4 plus 8 is 12, so this last number has to end in a 2, all of which are even because these numbers end in either 0, 2, 4, 6, or 8. Okay, now the next row, we're almost done. Here we go. A number that ends in a 6 added to a number that ends in a 0 has to end in a 6, even. Ends in a number that ends in a 6 added to a number that ends in a 2 has to end in an 8, the result. That makes it even. And then a number that ends with a 6 with a number that ends in a 4. 6 and 4 is 10, so it has to end in a 0, which makes it even. And then 6 plus 6 is 12, so the result has to end in a 2, which makes it even. And then a 6 plus an 8 is 14, so this number has to end in a 4, which makes it even. So you only have to look at the end digits. I don't care how many digits the numbers have. When you add two numbers, that what matters most is that it ends with either a 0, 2, 4, 6, or 8. And then the last one here, work ahead. Pause the video and try this one. See if you got it. All right. Pause the video right now, fill this last column in, and then check with me. Sorry about that, guys. Okay. Okay, so I'm assuming you did it, so let's try it. So a number that ends in an 8 added with a number that ends in a 0 has to end in an 8, making it even. A number that ends in 8 added to a number that ends in a 2. 2 plus 8 is 10, so this number has to end in a 0, which makes it even. Then 8 plus 4 is 12, so this number has to end in a 2, which makes it even. 8 plus 6 is 14, so this number has to end in a 4, which makes it even. And then 8 plus 8 is 16, so this has to end in a 6, which makes it even. So this right here, this is the last, these represent the last digit in the sum. The last digit, all right, in the sum of two numbers, of two even numbers, of two even numbers. And because of that, all of these ending digits are either 0, 2, 4, 6, or 8, which means that the results are all even. Okay, so the conclusion is that all the results must be even right here. All results, all right, must be even. Boom. And guess what? I just did that. Shows an infinite number of possibilities, which should blow your mind, guys, because I said it in the beginning that you can't list them all right? You can't list them because there's an infinite number of possibilities here. But you just saw a way to show that an infinite number of possibilities must be even. If you take an even integer plus an even integer, whether it's negative or positive, it doesn't matter. All right, the result must be even. So it's closed under addition. All right. Now the second way is to do it algebraically. Now this is the preferred method typically, all right? And it has to do with above here, okay, what we talked about earlier. I said that even form for any number n here is always 2 times k, where k is an integer, okay? So it's going to be 2 times some integer, even form. Okay, so what we want to do is take two different even integers. Okay, so here we go. This is the algebraic style proof that we're going to be focusing on uh, in our lessons. Okay. Okay, and don't be afraid of this. When I say proof here, it's not that hard. It just requires basic Algebra 1 principles. Okay, so what I do is I say all right, A and B, all right, let A and B be any two even integers. Okay, be any two even integers. You have to start with two different integers. A is the first one, B is the second one. Now, if that's the case, okay, let's say even integers here. If A and B are even, that means all right, A has to be equal to 2 times K, where K is some integer. Okay, so K is an element of the integer set, okay? If you don't like symbols, you can just write the word integer. Remember that symbol E here represents element of. So when I say K is an element of the integer set, that means K is an integer. And if you don't like using symbols, you can just say this. You can say K, okay, is an integer. Okay, if you don't want to use the symbols, that's what it means. Now, B is a different one. So B is equal to, you can't use K, you have to use some other variable, okay, because B is different. All right, so let's say use L. So where L is some integer, okay? So it's basically, we got these two integers, even integers, excuse me. Remember, 2 times an integer is even form. Whether it's 2k or 2l or 2m, I'm just using different variables because we have different numbers. Okay, and then what we want to do is show they're closed under addition. Show closed under the operation of addition. So under addition. So I need to add them up and see what happens. Okay, so here we go. So I take A plus B. Well, I add them up, right? Well, what's A? It's 2K. What's B? It's 2L. So I've got 2K plus 2L. That's my lowercase l. And what I want to do is show that it's even. And to show that it's even, I have to show that it's 2 times some integer. So what I do is I just factor out what's in common. Okay, so I factor out the 2. This is an Algebra 1 concept. So factor out the 2. So I get 2 plus K plus L. Let me just pull a note right here, factor out the 2. A little note. Okay, now, then I ask you, K plus L, is K plus L an integer? Well, K is an integer, L is an integer. And did we discuss this before in the previous activity in a previous lesson? Is an integer plus an integer an integer? So let me write it out in words. Is an integer plus an integer another integer? And the answer is yes, because we talked about that before. All right, an integer plus an integer is an integer. So this is 2 times some integer. And my friends, that's even form. Okay? Anytime you can write a number as 2 times an integer, you have even form, which means a plus b must be even. So, comma, so this is my conclusion, a plus b must be even. Now I'm writing it very specifically, all right, and I'm not skipping any steps, all right, so that you guys understand what's going on. And in the first exposure of this, there's with dealing with variables here, this is kind of abstract for a lot of people, and it's going to take a few days to understand and apply. So don't worry about it. We're going to be working with this over time. All right. And if you want to do yourself a favor, what I would suggest you do after you're done taking notes here is rewind it and listen to the Model 2 again and just focus in on the lesson and hear the listening, the logic, and the thought process behind it, and then go on, okay? So if you're not quite understanding what's going on, again, rewind the video, listen to it again, and then when you come to class, of course, I'll clarify and we'll practice. So these are two different models of how to prove uh, closure under an operation. And in the activity, which is 1-2 right here, we want to do the same things. So is the set of even integers, is it closed under multiplication, and so on. So you got to, again, the directions are up top, decide whether the following sets are closed. This is a closure activity. And you have to justify your work. All right, justify with a proof, okay, with a proof. So if you want to, you could start thinking about these and jot some ideas down, but we're going to work on this activity in class here. All right. So what I want you to do right now, after this right here, no, actually I'll talk about the next stuff later. All right. So this is Mr. Ainsworth right here. Once again, this is prep for activity 1C2, and I'll see you in my next session in MRWC. Take care. Bye-bye.